Hello, welcome to Lecture 7 of Electrical Circuits 1. At the beginning of the lecture, I'm going to do a quick review of the various circuit analysis techniques we've presented so far. That's going to lead us into talking about two new analysis methods. I'm going to give a quick overview of nodal analysis and mesh analysis. The remainder of the lecture will be spent discussing and presenting nodal analysis of electrical circuits. We'll do a couple of examples after I present the overall analysis techniques. The related educational modules are 1.6.0 and 1.6.1. Okay, so far we've presented a number of analysis approaches and analysis tools for electrical circuits. The first thing we did was presented voltage-current relationships. The only one we have so far is for resistors, Ohm's law. Later in the semester we'll present some other voltage-current relationships for inductors and capacitors, but this is all we have to worry about to date. We did a couple of Kirchhoff's laws. Kirchhoff's current law, the sum of the currents either entering or leaving a node has to be zero. And we also presented Kirchhoff's voltage law, the sum of the voltage drops around any closed loop in a circuit has to be zero. Now after that, we noted that if we applied these approaches blindly, we could do an exhaustive method of circuit analysis. But in a lot of cases, that led to a large number of equations and a large number of unknowns. So to simplify our analysis methods, we introduced circuit reduction. What we did is for a couple of special cases, parallel circuit elements and series circuit elements, we applied Ohm's law, KVL, and KCL in those special cases to get a simplification of the circuit by reducing the total number of circuit elements by creating equivalent circuit elements out of multiple other primary circuit elements. Now, there's something very important I have to note here. I claimed that circuit reduction was another analysis technique. It isn't. It's a special way of applying Ohm's law, KVL, and KCL in order to make your life a little bit easier. We didn't do anything new when we were doing circuit reduction. Now let's take a look at a quick example circuit and those previous analysis techniques in the context of this example circuit. Okay. For this circuit, I can't find a way to apply circuit reduction techniques to this circuit to get down to what I hope to get to in a circuit reduction technique is a single equation with a single unknown. I can't do that with this circuit. So based on our previous analysis techniques, I have to go back to applying KVL, KCL, and Ohm's law. To do the exhaustive approach, I would have to define a voltage difference and a current through each one of these resistors. That would give me 5 unknown voltages and 5 unknown currents. I would have a system of 10 equations and 10 unknowns, which is actually fairly painful to deal with here. We would like to take a look at some more general techniques to reduce the number of unknowns and the number of equations we have to write and solve to solve systems like this. So in order to try to help ourselves out with circuits like the previous one, I'm going to introduce two new analysis techniques. Okay? We're going to do what is called nodal analysis, and we're also going to do what is called mesh analysis. These analysis techniques provide a rigorous way to apply KVL, KCL, and Ohm's law, but in a way that reduces the set of unknowns that we have to deal with. If we reduce the set of unknowns, we reduce the number of equations we write, the overall circuit analysis becomes easier. Okay, next I'll provide a brief overview of the goals and the general approach for both nodal analysis and mesh analysis before we go into the details of how to apply nodal analysis. So our overview of a nodal analysis. In nodal analysis, we're going to identify a number of independent nodes in the circuit. Okay? The voltages at those nodes will be called the node voltages. Those are our unknowns in the system. Okay? What we're going to do is write KCL at each of these independent nodes and use Ohm's law to write KCL in terms of these node voltages. This will give us a number of equations that we can solve to determine the node voltages. So we'll have the voltages at all of our independent nodes. Once we've got those voltages, we can use those to determine anything else we want to know about the circuit. Okay, so we're writing a system of equations only for independent node voltages. Then once we solve those, we can find everything else we need to know. Overview of mesh analysis. Mesh analysis is in some sense the flip side of nodal analysis. What we're going to do is identify mesh loops in the circuit. The currents around those loops are what is called the mesh currents. Okay, those mesh currents are going to become the unknowns in our system of equations. What we're going to do is write KVL around each of these mesh loops. We'll use Ohm's law to write KVL in terms of the mesh currents. We can solve these equations to find the mesh currents. It turns out that anything else we need to know about the circuit can be determined from the mesh currents. Okay, there's one thing I really want to emphasize about nodal and mesh analysis. Like circuit reduction, we're not doing anything new here. We're applying KVL, KCL, and Ohm's law. Okay, we aren't doing anything different. What we are doing is identifying a reduced set of unknowns so that we don't have to write and solve as many equations as we needed to do if we just applied KVL, KCL, and Ohm's law in what is called the exhaustive approach. So we're streamlining our analysis, but we're still have the same basic ways to represent the rules governing the circuit. For the rest of the lecture, I'm going to talk about nodal analysis. The first thing I'm going to do is present the overall nodal analysis technique. It probably works best to present that technique in terms of a particular example. What I'm going to do is use the previous example that I did on my overview slides in order to present the nodal analysis technique. Step one of nodal analysis. The first thing you need to do is identify what is called a reference node. Okay? You will identify the voltage at that node as being 0 volts. Now, it doesn't particularly matter which node you specify as being the reference. What happens is that you are identifying a node that gives you the reference value where all your other voltages are calculated relative to. Okay? So for this particular circuit, you can identify anything you want as the reference node. I'm going to rather arbitrarily say that this is V sub R, and that's what I am going to consider to be 0 volts. Step two, we're going to identify our independent nodes. Those are going to be the nodes at which our node voltages are defined. In order to do that, we're going to do what is called killing our sources. Kind of a bloodthirsty term for just removing the effects of the sources. What we mean by that is that we are going to replace voltage sources with a short circuit, and any current sources are going to be replaced with an open circuit. After that's done, any remaining nodes will be identified as independent nodes. So this is our previous circuit. It had a single voltage source, a 5-volt source right here. I've killed that source by replacing it with a short circuit. Okay, our old reference voltage node was down here. It's 0 volts. Now, this node up here is not a different node than the one down here. This is not an independent node. So after we've done that, we can identify our actual independent nodes. This is an independent node, and this is an independent node. We can label the voltages at those nodes. I'm going to call this arbitrarily node A, which makes this voltage V sub A. And I'm going to call this node B, which makes this voltage V sub B. Keep in mind, this is not an independent node now. Step 3, we're going to replace the sources, okay? That will give us an ability to write down what the voltages are at what are called the constrained nodes. They are constrained voltages. Okay, I've taken my short circuit and I've put my voltage source back in here. I've already said that this node here is not independent, it's dependent upon this one. I can actually write the voltage here. It is 0 volts plus 5 volts. So V is equal to 5 volts plus 0 is just 5 volts. We know what that voltage is. It's constrained. Okay? So dependent nodes, okay, which were nodes that were removed by killing the sources, have constrained voltages. We can write the constraint equation here to give us the voltages at those nodes. They're not independent unknowns that we need to worry about later on. Step 4. Now we're going to apply KCL at each of the independent nodes, A and B. KCL is the sum of the currents at the node is equal to 0, so let me label all the currents in these elements. This one I'm going to call I1, this one I'm going to call I3, this one's I2, this one's I4, this one's I5. Okay. I'm going to assume that currents leaving the node are positive. So KCL at node A I1 is coming into the node, that's a negative contribution. I3 is leaving the node, that's a positive contribution. I4 is leaving the node, that's a positive contribution. Those have to sum up to 0. KCL at node B. I2 is entering the node. It is a negative contribution, negative I2. I3 is entering the node. It's a negative contribution, negative I3. I5 is leaving the node. It becomes a positive contribution, I5. Those sum up to 0. So those are KCL at these two independent nodes. Step 5. We're going to use Ohm's law to write our previous KCL equations in terms of the node voltages. Okay, I've accumulated in red my information from the previous slides, which tells me what my reference voltage is, this dependent voltage is, my independent voltages, VA and VB, and what I've assumed as far as all of my currents. Now I'm going to write these currents in terms of the voltages at the nodes. So I1, if it's positive this direction, it is the voltage difference, 5 minus VA over the resistance 1 ohm. I2 is 5 minus VB. That's the voltage difference over the 2 ohm resistor divided by the resistance 2 ohms. I3 is equal to this voltage difference, VA minus VB over 3 ohms. I4 is VA minus 0 over 4 ohms. And I5 is VB minus 0 over 5 ohms. Okay. Now I've run out of room on this slide. On the next slide, I'll go in and substitute these terms into my previous KCL equations. Okay, previously I said KCL at A gave me minus I1 plus I3 plus I4 was equal to 0. If I substitute my previous expressions using Ohm's law in for this, I get negative 5 minus VA over 1 ohm plus VA minus VB over 3 ohms, which is I3, plus VA minus 0 over 4 ohms, which is I4. That sums up to 0. Now I can group the multiplicative factors on VA and VB. I have a negative 5 over 1, which becomes a 5 if I move it to the right-hand side. Then VA, negative times a negative is a positive. This becomes a 1 over 1 ohm plus 1 over 3 ohms. Multiplying VA plus 1 over 4 ohms multiplying VA. VB, I have a negative 1 over 3 ohm term multiplying that. So minus VB times 1 over 3 ohms. All that's equal to the 5 that I got by moving this negative 5 to the right-hand side. So this is KCl at A written in terms of my node voltages VA and VB. Now let me do the same process for node B. KCl at B gave me a negative I2 minus I3 plus I5 is equal to 0 was my previous result. Substituting in using Ohm's law, I2 is 5 minus VB over 2, so I have a minus 5 minus VB over 2 ohms. Minus I3 is VA minus VB over 3 ohms. Plus I5, which is VB minus 0 over 5 ohms. That's equal to 0. Now let me pull out the multiplicative factors on VB. So VB multiplies a negative times a negative is a positive, so I have a 1 over 2 ohms. This VB is a negative times a negative becomes a positive, which is a 1 over 3 ohms. This VB is a positive 1 over 5 ohms. VA multiplies a negative 1 over 3 ohms. And that is equal to this negative 5 over 2. If I take negative 5 over 2 and move it to the right-hand side, it becomes a positive 5 over 2. This is my second equation, KCl at B. It is in terms of my unknown voltages, VA and VB. I now have two equations in two unknowns. I can solve those equations for VA and VB. Finally, step 6, we can solve our previous system of equations, two equations and two unknowns, in order to determine VA and VB. I'm not even going to pretend I can do that in my head. It turns out that VA is 3.53 volts and VB is 3.56 volts. Now, once I've got these two voltages, I can determine anything else that I want to know about this circuit. Okay? For example, I may not have been interested in VA and VB. I might have wanted to know what I3 was. Okay? Well, I3 is just VA minus VB over 3, which is going to be 3.53 minus 3.56 over 3. It's I3. If I need something else, oh, I don't know, I5. I5 is VB minus 0 over 5 ohms. I have a number for VB. I can determine I5. Anything else that I want to know about this circuit now, I can figure out. There are a couple of quick checks you can make on your results at step 5 in order to make sure that you didn't make some kind of silly mistake when you were setting up your equations. In general, if you have an equation for node X, okay, you will have some multiplicative factor on the node voltage for that node V sub X. That multiplicative factor will be the sum of all the conductances connected to node X. Likewise, in the equation for node X, you may have other node voltages in that equation. The multiplicative factor on those node voltages will be the negative of the conductances between node X and that particular node where the voltage is at. Let me illustrate that relative to the example that we just did. Okay, this is our previous example. We had node A and node B. When we wrote the equation for node A, the multiplicative factor on V sub A is this conductance, 1 over 1 ohm, plus this conductance, 1 over 3 ohms, plus this conductance, 1 over 4 ohms. I also had a V sub B term, this node voltage over here. The multiplicative factor on that voltage is the negative of the conductance between V sub A and V sub B, negative 1 over 3 ohms. Likewise, when I wrote the equation for V sub B, the multiplicative factor on V sub B is the sum of the conductances at node B, 1 over 2 ohms plus 1 over 3 ohms plus 1 over 5 ohms. We also had a V sub A term in the equation for node B. The multiplicative factor on the V sub A term is the negative of the conductance connecting V sub B and V sub A. So I have a negative 1 over 3 ohms. Ordinarily, when I'm doing nodal analysis, I won't go through all 6 of those steps in such a painstaking fashion. I'll take shortcuts. For example, it's extremely common to combine steps 4 and 5. When you write KCL, just go ahead and include Ohm's law at the same time. Also, if you want to, you do not need to be consistent on your current directions between different applications of KCL at different nodes. Okay? In the previous example, I was very careful about knowing which currents went into the node and which currents went out of the node. However, if you want to, and I'll illustrate this in just a moment, every time you apply KCL at a node, you can assume that all the currents are leaving that node and treat all those terms as being positive. It turns out that the negative signs will all cancel out so that it doesn't really matter. Let's take a look at what these shortcuts do when they're applied to our old example. Now, I've taken an intermediate step. I've already assigned my reference voltage node. I've determined my independent node voltages, and I've determined my dependent voltage. Now what I'm going to do is apply KCL at A using my shortcut approach. I'm going to assume that I1 is leaving this node, I3 is leaving this node, and I4 is leaving this node. So this current is VA minus 5 volts over 1 ohm plus VA minus VB over 3 ohms, which is the current I3 through the 3 ohm resistor, plus VA minus 0 over 4 ohms. That all sums to 0. Now, if I do the multiplicative terms on VA, I have 1 over 1 ohm plus 1 over 3 ohms plus 1 over 4 ohms times VA plus V sub B times minus 1 over 3 ohms is equal to 5 volts. Okay. Now, if I look at what I got previously, my equation for V sub A is the same as this one. V sub A times 1 over 1 plus 1 over 3 plus 1 over 4 minus V sub B, I put my minus sign in here, minus V sub B times 1 over 3 ohms is 5 volts. The minus sign that I originally had around this term here was offset by the fact that these two terms have swapped order now from what I did previously. I can do the same thing at node B. Now what I'm going to do is forget my positive directions that I had previously, and I'm going to assume that all the currents I2, I3, and I5 are leaving node B. That directly contradicts the assumption that I made about the current I3 at VA, but I don't care. So now KCL at B gives me the current I2 is VB minus 5 over 2 ohms plus the current I3 is the difference in voltage, VB minus VA, over 3 ohms, plus the current I5 is VB minus 0 over 5 ohms. That all sums to 0, so my multiplicative factors on VB are 1 over 2 ohms plus 1 over 3 ohms plus 1 over 5 ohms plus VA times my minus 1 over 3 ohm resistance is equal to minus 5 over 2 taken to the other side becomes a positive 5 over 2. So the equation for node B becomes the same as this one. VB times 1 over 2 plus 1 over 3 plus 1 over 5 minus VA times 1 over 3 ohms is equal to 5/2 of a volt. Okay, the signs have offset themselves. Everything's back to being hunky-dory. As long as you're consistent about your assumptions within every application of KCL, you're okay as assuming that all of the currents are leaving any given node. And in general, since I know I'm going to be making this assumption, I won't even label these currents when I'm writing KCL. It saves me a lot of time. Let's do another nodal analysis example. And when I'm doing this example, I'll go through it relatively quickly and take advantage of my previous shortcuts. I'll try to explain them as I'm going along. First step, I need to identify a reference voltage. Arbitrarily, I'm going to choose it as this bottom node here and say V sub R is 0 volts at this node. Now I need to identify my independent nodes. I'm going to kill my sources, okay, replace this voltage source with a short circuit, replace this current source with an open circuit. Any remaining nodes will be independent nodes. So I have a short circuit here where this 40 volt source was. I have a resistance there. I have a resistance there. I have a resistance here. I have a resistance here. I have a resistance here. And then I have an open circuit over here. The values of these resistors at this point don't matter. I'm just trying to find independent voltage nodes. Okay, this node is not independent of this node. I'm going to be able to label this as a dependent voltage. This 40 volt source is constraining the voltage difference between these two nodes. This node here, its voltage can be different than any of these other nodes around it. Let's call this node A and label that voltage as V sub A. This node here can also have a voltage different from this voltage and this voltage. Let's call this V sub B. You'll notice that I didn't say that the voltage here can be different than this voltage. I have an open circuit here. That means this current is 0. If this current is 0, the voltage difference across this resistor is 0 volts, and this node is not necessarily independent of this node. Okay. Later on, we'll take a look and see, okay, if you misidentify this and say that this is an independent voltage, what happens? And if you keep your wits about you, nothing bad happens because you remember that nodal analysis comes from KVL, KCL, and Ohm's law. As long as you're consistent about applying those, some of the details about nodal analysis don't matter. But at the moment, we're going to claim that the only independent nodes are here at V sub A and V sub B. I have two unknown voltages. I need to write two equations, which I'll do on the next slide. Okay, got my reference voltage node here. V sub R is equal to 0. I have identified V sub A and V sub B as my node voltages. I claim that this voltage source provided a constrained voltage, so the voltage at this node is 40 volts higher than the voltage at this node, so this voltage is 40 minus 0, or just 40 volts. Okay? I didn't identify this as a separate node, but I don't know the voltage because I don't know this voltage difference across a current source. We'll see how that plays out in just a minute. Now, if I do KCL at A, and if I assume that all the currents here are leaving node A, the current through the 2 ohm resistor is V sub A minus 40 over 2 ohms. The current through this 10 ohm resistor is V sub A minus 0 over 10 ohms. And the current through this 9 ohm resistor is V sub A minus V sub B, the voltage difference across the 9 ohm resistor, over 9 ohms. Notice that my voltage differences all are indicative of the fact that I'm assuming positive current is leaving this node. V sub A comes first in each of these expressions. These guys all sum up to 0, so I get, multiplying V sub A, 1 over 2 ohms plus 1 over 10 ohms plus 1 over 9 ohms plus V sub B, multiplying minus 1 over 9 ohms, is all equal to 40 over 2 is 20. This negative sign turns into a positive sign when I move to the right-hand side. This is 20 volts. Now that I've written this equation, let's take a look at a sanity check on it. The multiplicative factor on V sub A is the sum of the conductances at node A, 1 over 2 plus 1 over 10 plus 1 over 9. The multiplicative factor on V sub B is the negative of the conductance between V sub A and V sub B, minus 1 over 9. It doesn't look like there's anything obviously wrong with this equation. Now let me do the equation for node B. Now when I write my equation for node B, I'm going to forget that I had originally assigned some current directions here at node A. And now I'm going to assume that all of the currents are leaving node B. So if I apply KCL at B, my current through the 9 ohm resistor is going to be assumed to be that direction. The current through the 4 ohm resistor is going to be assumed to be in that direction. Let's forget about this one for the moment. So this current here is V sub B minus V sub A over 9 ohms. Ohm's law says it's the voltage difference divided by the resistance, plus this current here is V sub B minus 0 over 4 ohms. Now I need to find the current going through this 8 ohm resistor. When I was identifying independent nodes, I was claiming that I didn't need to know this voltage. Okay? The reason I don't need to know that voltage is if I do KCL here, the current through this 8 ohm resistor is 2 amps regardless of what that voltage is. You don't need to know that voltage in order to determine this current because of this current source here. 2 amps is coming in this direction. So I have 2 amps entering this node, becomes a negative 2 amps. I'm assuming currents out of the node are positive. That sums up to 0. Notice that current sources appear directly without any multiplicative factor on them. Therefore, multiplying V sub B, I have a 1 over 9 ohm resistance plus a 1 over 4 ohm resistance Multiplying V sub A, I have a negative 1 over 9 ohm resistance, and I move this 2 amp current to the right-hand side to make it positive. Double checking my results, okay, at V sub B I've got the conductances connecting it to the other independent nodes around it. At V sub A, I've got the negative of the conductance between V sub A and V sub B, and then my current source appears directly in the equation. I have now written two equations and two unknowns, which I can solve for V sub A and V sub B. Now, if I solve those equations for V sub A and V sub B, I get V sub A is equal to 30 volts, and V sub B is equal to 12 volts. Now, from those two values, I can determine any other unknown in this circuit. And my original problem statement said I wanted the current I through this 10 ohm resistor. I can determine that current by applying Ohm's law between V sub A and the reference voltage. So I is 30 volts over the resistance, which is 10 ohms, so I is equal to 3 amps. Now, I mentioned earlier when we were setting up this example that it wasn't really a big deal if you didn't notice that this was a dependent node. If you left it as an independent node and assigned it its own node voltage, it turns out okay in the long run as long as you're paying attention. So now we're going to say that V sub C is now a node voltage as well. We don't have to rewrite our equation for node A because the current out of node A doesn't depend directly on V sub C. Our equation for V sub B is going to change. So let's redo our KCL equation at node B. The current through the 9 ohm resistor is still VB minus VA over 9 ohms, assuming that the current is positive out of the node. The current through this 4 ohm resistor is V sub B minus, this was our reference voltage of 0 volts over 4 ohms. Now here, our current is V sub B minus V sub C over 8 ohms. That all sums up to 0. So we've written another equation that's comparable to the first one we did, except that we left an additional unknown. We now have two equations, but we have three unknowns. We have to write KCL at our node C. KCL at C says that the current out of node C towards B is V sub C minus V sub B over 8 ohms. Now we have a 2 amp source going into node C. That becomes a minus 2 amp contribution. That's equal to 0. So V sub C minus V sub B over 8 ohms is equal to 2 amps. We can take this equation, substitute it in for this term. So this term is the negative of this one. So we have a negative 2 amps here, which turns this version of KCL at B into identically the same thing we had before when we didn't have this additional unknown. Okay? As long as you're paying attention and you're consistent, things will work out. You may have a penalty of an additional unknown sometimes. It's generally not a very big deal. Let's do one last fairly simple example. I want to determine this voltage V across this 3 kilo ohm resistor in this circuit. Step 1, define a reference node. I tend to, by force of habit, choose it at the bottommost node in my circuit diagram. That's not a requirement, but let's say V sub R is equal to 0 there. Kill your sources and determine your independent nodes. This circuit becomes this. The 2 amp source becomes an open circuit. I have a resistance here which remains in place. The voltage source becomes a short circuit, and I have another resistor there. So I only really have one independent node. So I only need a single node. Let's call it V sub A here. Okay? Now replace your sources and label any dependent voltages. I have a 3-volt difference between this node and this node. If this voltage is V sub A, this voltage is V sub A minus 3 volts. Now I'm going to identify something called a supernode. Since these are not independent voltages, I only need to do KCL once here. Okay? So now if I take a look at the currents leaving this supernode, I have KCL at A. I have 2 milliamps going into this node here. That's a negative 2 milliamps. I have a current coming out of here. That current is V sub A minus 0 over 3 kiloohms. I also have a current going through this resistor. It is the voltage difference across the 6 kiloohm resistor divided by 6 kiloohms. That voltage difference is V sub A minus 3 is the voltage here, minus 0 over 6 kiloohms. So V sub A minus 3 is my voltage here, minus 0 volts over 6 kiloohms is equal to 0. This is one equation and one unknown. I solve that and get V sub A is equal to 5 volts. In that case, this V is just V sub A minus 0, so V is equal to 5 volts. Let's redo this last example with an alternate choice of reference voltage, just to show that that choice doesn't matter ultimately in my final solution. Last time I chose this lower node as being my reference node. This time I'll choose this as my reference node. Now I'm going to go through the rest of the problem the same way I did last time, killing the sources to identify independent nodes. The current source becomes an open circuit. That resistance doesn't change. The voltage source becomes a short circuit with another resistance there. So if this is my reference node here, this is a dependent node. This is my only independent node. Let me call that voltage V sub A. Now I'm going to put my sources back in and label any dependent voltages. If this voltage is 0, the voltage source here is constraining the difference in the voltages between this node and this node. So this node is 3 volts lower than this node. 0 minus 3 is negative 3 volts. Now I can go ahead and apply KCL at node A. I have 2 milliamps going out of this node. That's a positive 2 milliamps. The current through the 3 kiloohm resistor is V sub A minus 0 over 3 kiloohms. And the current through this 6 kiloohm resistor is V sub A minus a negative 3 volts over 6 kiloohms. That all sums up to 0. If I multiply this whole thing through by 6 kiloohms, 2 times 6 is 12, plus 2 times V sub A, plus V sub A plus 3 is equal to 0. So V sub A is equal to minus 15 over 3, or minus 5 volts. However, V sub A is negative 5 volts. If I am assuming that this voltage is positive relative to this one, that means V is equal to a positive 5 volts. It becomes the same solution that we had before. Our reference voltage node definition didn't matter in our final result. Okay, that concludes lecture 7. Next time in Lecture 8, we'll go back and re-look at node voltage analysis again, iron out some of the details. Then we'll move on to talking about mesh analysis.